So what I thought I'll do today is to just give you an overview about what are the recent advances which have happened in both planetary and Earth application, looking at the last few years, but also to talk about future opportunities and future challenges. So let me tell you first, why do we explore? I mean, why are we spending all that money to send these spacecraft to the planet? And so if you look at this picture, it's a picture taken from the Hubble telescope. And the area covered by this picture corresponds that if you take a cent and put it at the end of your arm, that's about the area of the sky which is covered by this. So it's a little teeny part, of the sky, and look at this variety of what looks like galaxies and stars. So if you extrapolate to the whole sky, there are literally billions and billions, of galaxies and stars. And then if you zoom on some of these galaxies, this is an example of a zoom on a couple of the galaxies that we have. And if you zoom even further on them, that's a galaxy which is similar to our galaxy. It's not ours, but it's similar to it. So imagine you have these billions of galaxies, and each one of them have literally billions of stars in it. Each one of these bright dots, is a star. And if you think about our star, which is the sun, it would be one of these little dots, in the picture here. And if you zoom on it, you see that actually there are planets around it. So again, remember, billions of galaxies, billions of stars, and on one little teeny one, there are actually these planets around it, and we are in the third planet from the left, in our solar system. What's amazing for us is when you zoom on that planet, which we call Earth, that's what you see. And it happened that on that planet, there have been the right chemistry, the right phenomena, the presence of water, the energy that actually led to creation of molecules. And then these molecules got together and this created the beautiful world that we live in after 3.8 billion years, of evolution. So you wonder, how did that happen? How did it start with a Big Bang 13 billion years ago? And then the planet in our solar system formed about 3.8 billion years. And through that evolution, it led to you and I having this interaction. How did that happen? What led to this? So what we are trying to do in our space exploration is to understand that development and that evolution from the Big Bang to life today, and then to understand how common is that. I mean, there is no reason offhand that this happened only on our planet, because there are literally billions of planets. And matter of fact, now every time we look at a star, we have developed the technology to look at planets around them or to detect planets around them. Every time we look at a star, we find that there are planets around it. Now, we don't know if there are planets exactly like ours. We don't know if life evolved in them. But just looking at the statistics of billions of planets and considering that the laws of physics and chemistry are the same across the universe, you would wonder, could there be other lives in other places? And if we detect life, it will change completely our thinking about our position. If we don't detect life, then you wonder, why did it happen only on this planet? So effectively, what we are trying to do is what I call to write the book of how did we start and how did we evolve and became where we are now, and what's going to happen in the future. So let me kind of give you a little tour about some of the exploration that we have done, and we're going to start with Mars. Mars gets particular interest because, number one, it's fairly close to Earth. It's between Mars and Venus. They are the two closest planets. Mars has a lot of similarity to Earth. It has polar caps that you see at the bottom, of the picture, and these polar caps expand and shrink depending on the time of the year on Mars. The year on Mars is about 2 years on Earth. You look at the geology, it looks very similar. We look at the early evolution of Mars. We believe that there was water on it, which I'll show you why we believe that. But also there are differences. Today, Mars is much colder than Earth. It has a thin atmosphere. So the question is, how did these two planets start and how did they evolve similarly or differently? So let me show you some pictures here. So here, one of these pictures is the Grand Canyon in the United States, and one of these pictures is the Grand Canyon, on Mars. And it's hard to tell which one is which. So usually in my class at Caltech, I usually ask for a vote. How many people think the one on the right is Earth? How many people think the one on the left is Earth? Even to make it more challenging, these are examples of two pictures, one taken with the rover on Mars and one taken in one of the deserts of California on Earth. And when I ask people how many people think the one to the right is Mars, about half the class raise their hand. Then when I ask how many people think the one on the left is Mars, half the class raise their hand, because it shows that the geology is so similar. Now, if you were in person, I would have taken the same vote with all of you. So I let you guess for 10 seconds. Now, I forgot which one is which, because they are so similar. But to be more serious, the one to the right is Earth. And the reason I can tell that is you might have seen a snake going across the image. If you were paying very careful, attention to it, there was a little snake which went at the beginning when it was moving, made across it. But the point I'm trying to make is that the geology is very similar. That means the evolution history of the surface is very similar. So now we have had presence on Mars literally since 2004. People don't appreciate that now for almost 20 years, we had the rovers continuously exploring that planet, day in and day out, 24 hours every day. And this shows a family portrait of these rovers at our lab at the JPL. So the one on the little teeny one, that's what we call the Pathfinders. That was a technology experiment we did in the late 90s. It was the first time we were doing a rover on another planet. The one next to it, which has these solar panels, that's a model of Spirit and Opportunity, which we launched in 2004. And they are about the size of your desk. The one next to it, that's Curiosity, which we launched about 9 years ago. And that's about the size of your car. And the one completely to the right, that's Perseverance. Perseverance, which is the one we landed about 9 months ago, last February. Now, the big challenge of these rovers that they are basically on them, they have the equivalent of chemistry lab at the university here. So they have a dozen of instruments, all compacted inside these rovers. And basically they have X-ray instrument, gamma ray instrument. It has ovens, so we can take samples with the arm, put them in the ovens, heat those samples to see what gases are being emitted from them. And then all that data is transmitted down to Earth for doing the detailed analysis on it. If there are some of you who are engineer-minded, all of these rovers, let me talk about the one we have the most recently on Mars. It's run on about 140 watts. So that's the equivalent of a light bulb in your office. So we have to develop electronics and instruments which are run on very small power. And they are very light because we have to compact them and put them in these rovers. And the wheel are run with electric motors. So it's like now that usually I kid people when they tell me about, the invention of electric vehicle. I tell them, well, guys, we have been running electric vehicles on Mars for the last 20 years, except they are a lot more expensive than Tesla and the electric cars that you have down here. So now let me tell you a little bit about the challenge of getting to Mars and the navigation challenges which goes with it. So typically, like Curiosity or Perseverance, after traveling 2 million kilometers, we have 200 million kilometers, sorry. We have to arrive within a circle of 2 kilometers on Mars. Now people say, well, what does that mean? So that's the equivalent as if you are in Los Angeles and you hit a golf ball towards St. Andrews in England, the ball has to go straight in the cup. That's how accurate that is. And to make it challenging for the good golfers, the cup is moving at 60,000 miles per hour because Mars is moving in its orbit. And we still have to get it in the cup. So that required a lot of development in navigation and targeting that we have mastered at JPL over many years. And we have to do somewhat similar, not this accurate, but somewhat similar to all our other missions. The other challenge is we are arriving at Mars at almost a speed of 60,000 kilometers per hour. So if you look at the energy in the capsule, which is arriving, The energy is equivalent to the kinetic energy of 18,000 race cars going at full speed. And we have only 7 minutes to dissipate that energy and land softly on the surface, otherwise we crash. So that required developing technology first of heat shield. So when we slam in the atmosphere, that slows us down. So that's similar if you are driving fast in your car and you stick your hand out of the window, you feel the pressure of the air. So we use basically the atmosphere of Mars to slow us down. Then we open a supersonic parachute, which is the largest parachute ever developed to slow us down even further, because the challenge on Mars is the atmosphere is about 1% the atmosphere on Earth. So it's the equivalent of being at about 100,000 feet. So the atmosphere is not enough to slow us down, so we land. Then we use retro rockets to slow us even down. And then we hover and we sky crane the rover slowly down to the surface. So it touches the surface very softly. And imagine all of that done on another planet. The time delay is about round trip 20 minutes, so you cannot joystick it. It all has to be done completely autonomously. And if one thing goes wrong, the whole thing is lost. So it's create a lot of tension and a lot of excitement when we do these things. So now let me show you some reality and describe to you a few things. That's the actual rover which is on Mars. That was in the chamber at JPL about 2 years ago. So it gives you an idea about the size and the sophistication in it. As you can see, everybody is wearing these suits because one critical element is we want to make sure we don't take any living matter from, on the rover to Mars and then say we discovered life on Mars. So everything has to be very clean, very carefully cleaned. And then even with the care of all the engineers, then we bake the rover, we clean it chemically. So we do everything possible to make sure that there are no or minimum amount of life or bacteria, on it. Now, to give you a little bit of an idea, you see in the top left that there are a red circle. So that's a camera, and it's a laser beam that shines through that telescope. And the laser beam is so powerful that it evaporates the surface of rock, so we see what's being emitted, so we can tell the composition of the rock. You see the arm is folded in here in the front. So that arm goes out, it has a drill on it, and it drills in the rock, takes some powder, put them in an oven, which is in the body of the rover, and heat that oven and look at what's being emitted. And all of this has to be done autonomously. I mean, we tell it ahead of time what we want it to do, and then the rover has capability to do all of that, autonomously. So now let me show you how do we package this and enter it, because you say, how do you take that rover, put it on the top of a rocket and get it to Mars? So look at the rover where it says rover. So that's the rover folded in. So we fold the wheels inside. So it's like we're trying to package it, like Songo was telling me, he has a packaged bicycle. So this is a rover or a car that you have to fold and package. Then we stick it under what's called the descent module. So that's where we have the retro rockets, and which are going to hover and then drop it with a sky crane. Then we put both of them on one side. We have the heat shield at the bottom, and the top side we have a back shell, at the top. So it's being protected. So when we enter the atmosphere, the heat which is generated is almost goes up to about 2,000 degrees. So the heat shield is actually protecting us for that. And then the whole package is put on what we call the cruise stage. So that's a spacecraft which carry it to Mars, pointed it toward Mars, and then drop it in the atmosphere. Now, you can notice one of the things we did on this rover, we had plenty of cameras to actually see how the parachute opens, how the heat shield drops. And so we'll be able to get information about how things were happening, delayed by 20 minutes, but to see what was actually happening. So this shows you actually all these pieces in what we call the high bay. So that's where we are assembling it. You see the rover being assembled. You see the descent stage next to it. And to the right, you see the cruise stage, which was carrying it. And you see a sign called Wall of Fame. So this shows all the pictures of the spacecraft that were actually assembled, in that high bay at JPL. So now I'm going to transpose you to the mission operation room at JPL and show you what actually was happening during the descent, and the landing on February 18, earlier this year.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
So now all what you're seeing is actually real. So this is when the parachute opened on Mars. We were looking up toward that parachute. I'll tell you later why are those colors, what do they mean?
Velocity is 480 meters per second at an altitude of about 12 kilometers from the surface of Mars.
And now you are looking down and you see the heat shield being dropped, and that's Mars in the background. So this is all real. So it's like if you were sitting on that rover watching what's happening as we are going down on Mars. You see the heat shield in the horizon going down.
9.5 kilometers above the surface.
And now, as I told you, we had only by now we have only 3 minutes or 4 minutes left. So this is all in real time. So I'm taking you on a trip traveling to Mars. And one challenge we had here is we wanted to land in a very specific area. So we had to look at the images, the rover autonomously, look at the image and move its trajectory to match toward the specific area we wanted to land. So that's why you see it going back and forth, and it's sitting on the parachute. So it's oscillating back and forth at the bottom of the parachute.
Is continuing to descend on the parachute. We're coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
And we are measuring the distance with a radar instrument.
Yes, valid. We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars.
Yeah, then we separate the parachute. So now it's coming down in free fall.
Maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
Here on safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars.
So now you see the retro rocket firing. And as we get close, you can see the plume.
About to conduct the flight crane maneuver.
And now we are hovering, and you can see at the left, we are sky craning the rover. At the bottom, we are looking down. At the top, we are looking up. And then when the rover touches the surface, we cut that cord so the retro rocket will fly away, like you are seeing it here, and the rover is on the surface.
The surface of Mars, ready to begin seeking the sands of past life.
So anyway, you could imagine the excitement in that room, because just think about it. People have been working on this mission for literally 8 years. And everything depended on those 7 minutes. Either everything will be great success, or it will be a complete failure. So the tension is extreme, and the excitement is an extreme too. So the first thing we do after we land, we have on the rover itself, we have about 16 cameras. So we first take pictures, send them down to make sure everything looks fine. So this is a camera which is under the belly of the rover. And you can see the shadow, the shadow to the right, that's one of the wheels, shadow on the surface. So that's the first thing we do is like when, somebody or your mom or your dad give you a iPhone, you take a picture and say, look, Dad, how nice I look, on this thing. So that's the first thing we do. And that's where you see, then we start testing over a period of a couple of weeks. We start testing the different element, to make sure everything is working fine. So here we're testing, turning the wheels around. This is the arm which has the drill on it. So you can see it here. We're again testing it to see how everything is working well. Oops. Okay, so that looks we got back. Oh, maybe we'll go back. So let me tell you a little bit what's the purpose of this mission. The purpose of it is to drive around Mars over a period of 3 years, and with its scientific instrument, decide what are the most interesting rocks or material, drill through them, take samples like you see to the left, put it in a sample tube, seal it, put them in a cache which has 31 slots in it, and put the whole cache in one location. So a few years from now, we're planning to send another lander, grab that cache, that box, put it in a nose of a rocket on Mars, launch it, put it in orbit around Mars, and have a spacecraft rendezvous with it and bring those samples back to Earth. Just piece of cake, no problem. So this will be one of the biggest challenges that we ever have done. And the key thing is to look at rocks which could be potential habitable rocks. Now, what does that mean? That means potentially in area, we landed in area where we see what we call alluvial fans. That means these are areas which have been formed by flowing water, which could be a possibility that life could have evolved in them. So because we see channels on Mars, we see alluvial fans, the geologists who are on this presentation, would know what that is. We see dry lakes, we see the salt in dry lakes when the water evaporates and then the salt is left. So we believe that early days of Mars was similar to Earth, or was flowing water on the surface. But for some reason, that we have potential hypotheses, Mars cooled much faster than Earth, lost its atmosphere, so the water became frozen below the surface. And that happened over many hundreds of millions of years. So the question is, could have life evolved during those early 100 million years like it happened on Earth? And could we find them in those samples? Or are these samples habitable? And the best way, even that we can do a lot of analysis on the surface, the best way is to bring them back to Earth and do detailed analysis at laboratories here on Earth. So that's the main objective of this mission. So this is an example, of the panoramic view over that area. And now, sometimes people will ask, why does there color, on that parachute? Always on every mission, we do some kind of a clever trick on it. So in this case, what this is the code on the periphery. That's the longitude and latitude of JPL. So JPL latitude is west 34 degrees, 11 minutes, 58 seconds, and north 31 degrees, 10 minutes, 118 seconds, or vice versa. So like that, if any Martian picks that parachute, and if they are smart enough, they will know where it came from. And in the middle is a logo that I had started at JPL to reflect the nature of JPL, which is their mighty thanks. Because these are the kind of things that we do. I copied that from a Teddy Roosevelt quote. And that's the kind of thing that we pride ourselves at JPL, that we really don't go and do routine thing. We just dare the most difficult thing, we dare doing them. Even that every once in a while we have some failures, but that's how you move the frontier of knowledge and science. And that's a message to all of you who are listening here, that you should in your career and your research and whatever you are doing, is always try to push the limit. And don't ever take something that looks impossible to be really impossible. Many of the things we have done, they looked impossible. But with dedication and smart people working on them, I think you can accomplish amazing things. Now, one special thing which was on this rover, on the latest one, we added a little helicopter on it because that allows you to fly. Now, you would say, well, what's a big deal? We have drones, everywhere. Well, the big deal is that, as I told you, on Mars, the pressure on the surface is about 1% of the pressure on Earth. That's the equivalent of flying at 12,000 meter altitude. Nobody has ever flown at that altitude, with a blade kind of thing, or airplane or jet airplane. Mount Everest is 8,000 meters. So we are flying at literally the equivalent of 30,000 meter altitude. So that required developing a helicopter which is extremely light. That helicopter I showed you weighs about 1.5 kilograms or 2 kilograms. And in that 2 kilogram is everything: the electronics, the camera, the communication link, the blades. So we had to develop all kinds of special electronics to actually being able to do that and to spin the blade at many thousands of rotation per minute. So it was a big challenge to do that. And when we first proposed that to NASA, they thought we are smoking something. They said, what in the heck, do you think really you can do this? So anyway, it was the engineer, with their commitment and dedication, we developed it, we tested, in our chambers at JPL, and we actually successfully sent it to Mars. So that show you the actual flight article, on the right, and on the left is a chamber, at JPL, where we were able to simulate the environment of Mars. So we empty the chamber, it's a sealed chamber. We empty it, have a pressure of 1%, and it's all the gas in it is carbon dioxide to simulate the Martian atmosphere. The only thing we couldn't simulate exactly is the gravity on Mars, because it's about 1/3 the gravity on Earth. So we did a lot of testing to make sure that we'll be able to run this mission. And now I'm going to show you literally the first time ever that a helicopter or an airplane flew on another planet. Look at the bottom left. So the rover was taking the picture. So this is the equivalent of the Wright brothers on another planet. So, and we did some testing. So you see the helicopter moving, in the sky on Mars. Maybe the Martians are hiding behind those hills, watching it. And the helicopter will come back. So if you wait for a few seconds, it will come back. But to give you an idea, we were able to convince NASA to add it as purely a technology experiment. So we promised that we will do 5 flights. And if we do 5 flights, we are successful. Well, yesterday they had flight number 16. And now it's not only a technology experiment, but it flies ahead of the rover, surveys the areas like a scout, sends the images to the rover sends the images to Earth, so we can decide where are the most interesting areas, so we can drive toward those areas. And one of the key challenges, I remember how small it was, the flying was already a challenge, but another key challenge was actually the landing, because we have autonomously, the helicopter had to look at the surface and decide where to land, because we don't want to land on a big rock and tip, and then we lose the mission. So there was a lot of, if you want, semi-intelligence in that little 2 kilograms, helicopter, which have to be developed. And this is an example of a picture from the helicopter. So it shows the track of the rover, and you see at the bottom in the middle, so that's a shadow of the helicopter on the surface of Mars. And this is an interesting picture, because a picture from the helicopter of the rover. So it's looking at its mother ship here, because the rover carried it to Mars, and that's where we help guiding that rover using this data. So now let me move away from Mars, even that Mars takes a lot of attention, but we have spacecraft all over the solar system. This is a mission called Juno, which is spacecraft in orbit today around Jupiter. And these are pictures of Jupiter taken from that, these are natural colors. So you are actually saying, if you were on that spacecraft, that's what Jupiter would look like. Oh, sorry, this was taken from the Hubble. Sorry, I'll show you the picture from, and that's a picture of one of the satellites of Jupiter that we took, which is called Europa. And this satellite is about the size of our moon. It's made of ice. So the surface is completely water ice, H2O, like you put in your cup. And you see this brown material, which are organic material. And you see this fracturing on it. So based on the fracturing and on measuring the gravity and the magnetic field, we believe that there is an ocean just below the surface, on Europa. Because you look at, if you zoom and look at the detailed picture, you see what look like ice flows. So these ice flows are about 5 kilometers in size. So it's similar to what you see over the polar caps when you are traveling from here to Europe and you fly over the North Pole. And you can see some of these features at the boundaries, they are displaced. So that all gave us an indication that this ice, which is floating on an ocean, on a liquid ocean below it. And from the size of the ice flow, we are guessing that the ice thickness is about a few hundred meters. So immediately the question then comes, if there is an ocean below the surface, if it's made of H2O, if it had organic material, could life evolve in that ocean? So now we're planning a mission, which is called Europa Clipper, which will be launched in 2 years from now, where we will have on it a radar instrument which will sound the ice to determine exactly how thick it is, because we are looking for an area where the ice is relatively thin. And then we're planning later to put a lander on the surface, drill our way through that ice, and put a submarine under the ice to search for life in that water. And this is an example of what that kind of submarine would look like. So you think about it like an upside down rover. So it will be like what you saw in Spirit and Opportunity and the rovers. And it will float up and it will drive upside down, driving on the ice, but from the bottom. And then it will have scientific instrument. This is actual hardware, and this was put in a lake in Alaska, which was frozen on the surface. We got it below the surface, and it's driving and making measurement and transmitting all that data to JPL from Alaska down to JPL. So hopefully 10 years from now, you might see something which is on another planet, on Europa. Now, let me bring you back to our planet and tell you a little bit about what we are doing here, particularly being in an Earth Observatory Center. So we have about half a dozen spacecraft from JPL around our planet. Total, maybe there are many, many dozens of spacecraft. And I'm focusing particularly on global change and what's happening on our planet. We have been monitoring the ocean height since 1992. So we have a record of almost 22 years of the height of the ocean relative to a geodetic reference. And as you can see in the bottom right, actually the ocean is rising at a rate of few millimeters per year. So after, in this case, over a period of 2 decades, the ocean has risen almost a meter. So if you extrapolate for another couple of decades, there could be significant rise. And if that continues, you are going to have many places flooded, and a particular importance for Singapore being such a low altitude place. Now you say, what's the reason of that ocean increase? Well, there are 2 things which are leading to it. Number one is as we are warming, the ocean is warming, and with 1 degree of increase in temperature of the ocean, actually it expands by about half the amount that you see here. So half of it is coming from direct increase in the temperature of the ocean. The other half is coming from another experiment, satellite we did, which is measuring how much ice is melting in Greenland. And as you can see on the top right, actually there are gigatons, literally hundreds of gigatons of ice is melting over Greenland. And you can see from the plot, you see melting during the summer, then it freezes in the winter, then it melts and you have more snow in the winter. But on the average, the ice is really melting and it's all going in the ocean. And when you do the calculation, that accounts for the other half of the increase in the ocean height. So we have both measurement of the height itself and also measurement of what is causing it. So when I talk people who are skeptical about what global change is doing, particularly people in Congress in the US, all what I have to do is to show them these two plots and these 2 pictures, and many of them become convinced. And these spacecraft are continuing and monitoring the environment around our planet, and they are being done internationally. The one about the ocean height is a joint program with the French Space Agency, and the gravity mission, which is measuring the amount of mass being melted, is being done jointly with the German Space Agency. Now, let me tell you about a satellite, which I think you all are going to be or many of you will be very much involved in it, and Sango was a major player in it. And that's a mission which is called NISAR for NASA-ISRO India Synthetic Aperture Radar. So basically, that will be a mission which is using a synthetic aperture radar, which will image the surface using microwaves. That means you can image it independent if it's day or night, and it uses its own illumination. So it doesn't matter if it's cloudy or not, because the microwave penetrates through the cloud. But this mission will allow us to do global mapping of our planet literally every other week. So you'll have a map of the whole planet every other week at resolution of about 20-25 meters. And also has the capability to interferometric measurements. That means it will allow to measure changes which are happening every 2 weeks down to fraction of a, or let's say a centimeter. So you'd say, what would change on that scale? If you have tectonics motion, we'll be able to measure it. If you have stress and bending, we'll be able to measure it. How much displacement happened after earthquake, we'll be able to image it. What happened if there is natural catastrophes, like mudslide, you'll be able to determine that change. How fast are the glaciers are moving? You'll be able to determine that change. Changes in the thickness of the biomass, the forest, and you'll be able to measure that change. So this mission is going to provide an amazing amount of data for geoscientists and users also that could be used. And I think the Earth Observatory will be a major player in the data analysis. Now, a key challenge clearly is getting the data, but we know how to do that. But the key challenge is that this mission will provide the data is about 10 terabytes per day. So just imagine the amount of data will be coming. And then how are you going to process it, analyze it, and make it available both to the science community and to the user? So it's going to require a lot of development in artificial intelligence, artificial analysis. So there is a whole richness of new development which has to come with its mission. Now, this will be launched in 2023. 2022 was the original date, but recently there have been a delay to do it in 2023. And this is an example of some of these images. This is based on presently orbiting European satellite, where we got images before an earthquake and after an earthquake. And then we combine them coherently using interferometric technique and determine the actual motion which have happened as a result of the earthquake. And this is another interesting, I find this one is particularly fascinating, because as we were measuring these changes over a period of, in this case, 6 years, we see the surface in Los Angeles actually breathing up and down. And the reason that's happening, because as you are pumping water from the aquifer, there is a little subsidence on the surface, and as the water is being replenished, then there is a little rise in the surface. And look at the scale. We are talking of centimeter here. So this mission, as we be doing global, we will be able to look at the Earth as it breathes everywhere, what's happening. And I'm sure, you'll be seeing here in Singapore, you'll be able to monitoring the changes, the subsidence and the rise, which is happening on the scale of centimeter. Now, another kind of interesting thing that also these radars are capable of, because we use microwave, we actually can penetrate through the surface down to about a few meters, particularly in dry region. So this is an example of data that we took a while ago. And at the top, it was from the shuttle. You see a camera imaging the Nile. And at the bottom is the radar image. And you can see where it's a Nile paleo channel. That used to be the old drainage channels of the Nile. But then for some reason, old meaning many thousand years ago, some reason it changed its path. And when the sand came and covered the old drainage channels, now you don't see it. But with the radar, you actually can see the old drainage channels. And we have done mapping of all of North Africa, and we have been able to look at where were the rivers in North Africa 6,000 to 10,000 years ago by penetrating through many meters, of the sand. And that's mostly happens in areas which are very arid, because then you have better penetration below the surface. And I thought I'll give you a little bit, think of fun things that we did. So these are from many of the field trips that I've done. At the top left, that was in Egypt. It was in the Sahara, roughly at the boundary between Egypt and Libya. The other 3 are taken in Oman. Let me tell you a little bit anecdote about them. So the one at the top left, we were a group of geologists from JPL, Geologic Survey in Egypt. We had to drive literally 300 miles across the desert to the area where we saw some of these channels, and we wanted to dig and verify that actually these are actually channels that we are seeing below the surface. So we had a group of like 50 Egyptian workers who went with us. They went, deployed the tents, in there, had to carry all our water or our food. And for the food, when we spent like a month, we needed to get some fresh food. So what they bought live ducks, because it turned out that ducks can sustain the heat very well. So they can survive in the heat. So one day we were asking the cook, because he had the duck in his tent. So we were asking the cook, how can you sleep during the night? These ducks are very noisy. He said, oh, it's no problem. Whichever is the noisiest duck, that's what you get for dinner that night. He said, after a few days, the ducks get very quiet on doing that. It's a true story. That's what he told us. Now, the other pictures are taken in Oman after we showed that we can actually do penetration and over the sand. A number of archaeologists approached us about potentially looking at ruins of city or caravan passes. And one which attracted our attention was a mythical city of Ubar. So if any of you kind of remember from the Bible, there were the three magi, which one of them brought frankincense from the city of Ubar. So to make a long story short, we actually were able to discover the remnant of ruins of that city. And then it ended being a 20-year archaeologist, over 20 years have been digging for it. And now if you go and Google Ubar, you will see that it's part of the Omani site for tourists. And one of the fun things of working at JPL, you get to meet a lot of actors and actresses who are either interested in science or doing movies about it. Jacques Cousteau, I like to show this picture to show you how I looked like, when I was in my late 20s, early 30s. The one to the right is Prince Andrew. I don't know, he's controversial now, but in those days, he was not as controversial. At the bottom, Jessica Chastain and Matt Damon are the two actors who actually did the movie Mars. So they came and spent time at JPL to watch how we operate, our spacecraft. So it was a great movie. And I imagine some of you know Jim Cameron, that he did a lot of the science fiction movies today. And just to end, I retired from JPL 5 years ago. And one of the gifts that NASA gave me for my retirement is to rename the mission operation room as Charles Elachi Mission Control Center, because I spent a lot of time in that Mission Control Center. And in my closing note, I always use this word, "their mighty thing," that you saw on the parachute, because the quote goes something like this, and I find that very inspirational. And as I said, it's from Teddy Roosevelt. He said, "It's far better to dare mighty things, even though checkered by failure, than to live in the twilight which knows neither victory nor defeat." Because the only way you can advance is by pushing the limit. And when you are pushing the limit, failures are going to happen. Because if everything succeeds, that means you are not trying hard enough. So these are not tough things, enough. And the best way of savoring the pleasure of a success is to have lived through some failure, because it really will show how great and the benefit of that success. So that's something that now is on all the buildings at JPL. People use it in their email. So I would urge all of you to never hesitate on daring mighty things. So again, thank you very much.